All right. Back to work. So I want to do another example, one more, but more concrete, particularly applied to a program. And when you have recurrence relations, you have two kinds. One is called a decrement and conquer, which is basically this kind here, where to define R sub n, you use R sub n minus 1. Like in this case. 1 is defined in terms of 0, 2 is defined in terms of 1, 100 is defined in terms of 99. This is called decrement and conquer. There is another one where you split this in half. So to do 100, you compute, you use R of 100, you use R of 50. And to do 50, you use 25. And to do 25, then you run in trouble because you can divide it by 2. But basically, you do 12 and 13. So let's look at an example of this, where this comes about. Also because it's very interesting. Merge sort. First, let me remind you what is merge sort. Suppose that you have to sort an array, and I'll make it a power of 2. So there are 8 elements. And let me put a number at the top of my head. 3, 6, 1, 5, 4, 7, 8, 2. All right? So first, you split it in 2 parts. Here is one part, 3, 6, 1, 5. Here is the other part, 4, 7, 8, 2. Then you sort these two by a recursive call. So the algorithm that is supposed to sort the 8 number, you call it twice for the 4. This is the beauty of the recursion. This becomes sorted. 1, 3, 5, 6, and the other one will be 2, 4, 7, 8. This is the recursive call. And now you merge. So you look at these two, which is the smallest. Of these two, the smallest is 1. So you output 1 and you cross it out. Now you look at the two first, which is the smallest. 2. So you put the 2 here and you cross it out. 3 and you cross it out. 4 and you cross it out. 5, 6, 7, and 8. All right? So here we want to compute the running time. So the size of the input, of course, is how many elements you have to sort. What is a good operation to count here? Can be the comparison. How many comparisons we made? In this case, surprisingly, we made 6, I think. Well, not really for every element, because we, at some point, we output the 6. This is empty, the first half. So now we don't compare anything anymore, right? So I think a better operation to count is when you copy from the array above to the one below. Because you needed to really do storage. There is really a moving in memory of this. All right? So, what is the base case? Yes?
It's already sorted.
Well, the base case is when you have one element or 0 elements, right? In that case, how many operations you do? 0, right? We usually have to check whether there is a 0 element or 1 element, right? So maybe we should count 1 for 1. So here I would say R of 1 is 1. You with me? So now R of 2n. I wanted this to be power of n. So I don't know yet how to write it here, but let's start with 2n. In this case I have 8 here, right? What is this one? I sorted the first half and I sorted the second half. So this will be equal 2 times R sub n, right? This is the effort, the number of steps for sorting these two. And now, how many steps I need to merge? 2n. Yeah? And of course, this works well if I have a power of 2. So, 8, 16, 32, or whatever it is. Should we try to solve it? All right. So, in this case, I start from a larger number. And maybe I start from 8 or 16, just to get a hang of how things go. All right? So, what is R of 16? 2 R of 8 plus 16. So, what is R of 8?
2 R of 4.
Plus 8. All right? So, if I move this one here, because R of 8 is twice, what do I get? 4 times R of 4, right, plus 16. You with me? Plus 16, this one here, and the other one is twice this one. Yeah? So R of 4 is equal to what? 2R of 2 plus 4. So if I put this here, what do I get here? I get A R of 2 plus 16. Very good. And so now R of 2, what do I get? 2R of 1 plus 2. Because I have 8, what do I get? 16R of 1 plus 16. Yes? And now, R of 1, we said, the only operation we do there is just to see that is less than 2, so there is nothing to do there. You with me? And so, at this point, I have 16 plus 16. How many times? How many do I have? 5. Yeah? Yes? So who wants to make the miracle here? So here I'm saying this one. R 2 to the n. R 2 to the n is equal to what? 2 to the n, how many times? N plus 1. This is a big miracle. So if you play with this one a little bit, maybe you can convince yourself that this formula is okay. You can prove it by induction, which of course is not an easy task. Or you can try it for 4 and see whether it works for 4, for 8, for 16, for 32. If it works for a few, it works for all. And so now, suppose that you have an array of k elements. So you have R sub k. What you get here, when k is a power of 2, you get R sub k is equal k times logarithm the base 2 of k plus 1, which is exactly the performance running time of merge sort. And this is why merge sort is so nice. No matter how the elements are in your array, it guarantees this time. Quick sort typically does better than this, sometimes by a factor of 2. But once in a while is a disaster. There are n squared, and if n is big enough, you wait a very long time to do that. Up to the point that in some real-time situation is prohibitive. So you are much happier to take twice as much, but you are guaranteed that you never go over this event. So so good? All right, so you see this a little bit more in context. With this one, we are done with the sequences. I close this spreadsheet. Yes, thank you. I close this one. I close the solver. Let's go back to the schedule. So we are done with sequences, and so I assign homework number 4. And I will put it there when it's due, which is due next Monday, 1 week from today. As I said, that there are 2 versions. Let me show you the difference between these 2 versions. This is the regular one, which is like those you have been doing so far. This one has extra problems because some people ask for extra problems, and you don't have to do it, and you don't get any points to do it. So let's look at this one. First problem, this is the summation, the one we have been doing so far, and I'm asking you those 4, and I give you some possibilities. You have to pick which one is the correct one. Far so good? No surprises? The second is the same, exactly. But then it says, look, the summation goes from 1 to n. Try instead 0 to n, or 0 to n plus 1, or 1 to s plus 1, to n plus 1. You can add or remove 1 at the beginning or 1 at the end. So this is 2i. Instead of 2i, try negative 2i, or negative 1i, or 0i, or 1i, or 3i. And it's plus 2, again, instead of plus 2, say minus 2, or minus 1. or 0, minus or plus, doesn't matter, or 1 or 3. And so now, if you try all the possible cases, this is exponential. You have a 4 times 5 times 5. So, problem number 1 now, instead of having one problem, you have 100 problems if you do all the cases. If you want to know whether you got it right or not, what do you do? Say it again?
You're the solver page.
Fine, fantastic. The one, you go to the solver and it does it. The other one? Excel, you test it. Excel or also by hand. You test it here, right? Now, you can even test those formulas, right? Without solving anything, you see whether you plug 2 in n and worse without knowing anything about solving this one. There is no point in doing that. Here, we are trying to learn a technique, so you should apply the technique and see which formula you get. This is the sense of doing it. All right. The next one is the same. We learn the Gauss technique or proof to add this one, right? And so here I say go from 45 to 60. And instead of 45, you can try 35 or 25 or 40 or 22 or whichever number. Again, you get dozens or hundreds of similar problems. Some people may benefit to do more than 1, 2, 3, or 4. Of course, so once you understand it, they are all the same. So there is really no benefit doing more than the number you need to understand it. So I hope this will help a little. All right. So we are doing more interesting things. Counting. We have some structures, and we want to count how many elements are in that structure. So the first one that is discussed there is the intersection of two sets. You have two sets, A and B, and below you have an example. And you want to know how many elements are in the union of these two sets. Here we have a condition that the elements that don't have any, the sets don't have any element in common. So the intersection of the two sets is empty. How many elements there are in the union? The sum of the element of one plus the sum of the element in the other. Here we have a situation which is a little bit more complicated. It's the same, but we remove the condition that the intersection is empty. And so in the example, you see that here you have 3 and 4 in the first set, and 3 and 4 in the second set. How is going to play this? Look, the sum is all the elements, the number of elements in the first, plus the number of elements in the second, take away the number of elements in the intersection. Why that?
So we don't count the same number twice.
Fantastic. Both correct. If the intersection is not empty, when you count the element of one set, there is an element in the intersection, you count for this set and you count it for the other. So that one you count it twice. So to take away one of these two counts, and you take away the one that are in the intersection. This is the rule of the product. says if you have a Cartesian product, how many elements are in the Cartesian product? In the Cartesian product you have pairs. So this is the number of elements you have in the first set times the number of elements you have in the second set. Why? Because for each element of the first set you make a pair with any element of the second. And so this one will give you the product. If instead of doing the Cartesian product of two sets, you do the Cartesian product of n sets, then you have the product of the first, the second, the third, and so on. If all these sets are equal, you get this power notation here, which is very nice and very elegant, and also tell you why we write it in that way. All right. So here I have my pens. Suppose that I have this one and I want to count them. What does it mean to count them? Well, it means that I put them here and then I say 1, 2, yes, 3, 4, and 5. So basically what I'm doing here, I'm doing an injection, actually this is a bijection, between the elements of my set and the natural number. Here I start from 1 instead of 0. So don't be too paranoid on this. Here I can change it and I say 0, 1, 2, 3, 4. And the number of elements is the last one plus 1. So I get the 5 again. Particularly computer scientists, they shouldn't get too paranoid about this. Because you are familiar with arrays, that the first element in the array has index 0, right? So everything works out nicely. And so now we have a very interesting concept. It seems kind of trivial, and on this one we will discover incredibly interesting things. We say that a set is countable, which has the word says you can count the element if there is an injection from this set to the natural number. Exactly what I wrote on my piece of paper. If there is a bijection on top of an injection, we say that the set is countably infinite. All right? Countably infinite. Very interesting because we are going to talk about infinity. And infinity was the domain of philosophy and religion until not long ago. And then in the 1800s, people made incredible discoveries about this. And infinity became the domain of math. Yes?
Does chemically infinite also apply to like n plus, like positive natural numbers or negative natural numbers?
Any set. Any set that we say that is countably infinite if it is a bijection with n. Now we are going to see a bunch of examples. All right? Even numbers. Are the even numbers countable?
Yes.
Yes. Why? For many reasons, but a trivial one is that you can count them. 0, 2, 4, 6, and you keep going on. You are counting them, right? All right. So, how do we prove this one? We have to provide an injection. we have to provide an injection from the even numbers to the natural numbers, and I wrote it there. F of x is equal x. This is an injection. You with me? Does it prove that the even numbers are countably infinite? No. Very good. Why not? Because it's not a bijection. To prove that something is countably infinite, we need a bijection. All right? Can we find a bijection? Yes. What is the bijection? F of x is
1/2
x divided by 2, 1/2 of x. Now this is an injection and this is a bijection. And so it's countably infinite. All right? The integers. Are the integers countable? Yes, they are. It's written there. Now we are going to see it. This is less obvious, right, that there is an injection. Why? Well, very loosely speaking, I'm talking with my hands. Because for every two integers, there is a natural number, right? Loosely speaking. Natural number, there is 7, integer, there is 7, and negative 7. So it's not obvious that there is an injection. We have to put it together. And there is the definition. F of x is equal to what? To x if x is even, minus 2x minus 1, otherwise, meaning if x is odd. Should we write it down to convince ourselves that this is an injection or a bijection? Let me write it on the right side here. Forget this one that I did before. Sorry. So, here I have the integers, right? Negative 2, negative 1, 0, 1, 2, 3, dot, 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 dot. So, let me bring back the formula and write near your integer what is the result. So, for the even number, negative 2 is mapped to negative 4 because it's 2x. 0 is to 0 because it's 2x. 2 is 4 because it's 2x. Right? For the negative, what do I do for the negative? Negative 2 minus 1. So, negative 1 times negative 2 is 2. Minus 1 is 1. What about 1? So I think I blew the example, right? Right, I have to map it to the natural numbers. So, we have to find a better one. All right? So, negative 2, negative 1, 0, 1, 2, 3. Yes?
If you map all of the positive integers to the even natural numbers and all the negatives to the odd natural numbers.
Right, this is what I wanted to do, but I wrote it wrong. So basically, I want to map this to 2, this to 4, this to 6, and these to the one in between. So this maps to 1, and this maps to 3. Yeah? And 0 maps to 0. All right? So if it is a positive, it's double. So what I wrote here, positive and negative. So here I wanted to say if this is greater than or equal to 0, and instead I wrote even. All right? I fix it. And so this proves that there is a bijection between the integers and the natural numbers, so they are countably infinite. Yes? So now, a difficult problem. Suppose that I have n cross n. N cross n. Yeah? What are the elements here? 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, 2, 0, 2, 1, 2, 2. Is this countable? Can I find an injection? And even more, can I find a bijection between this and the natural number? Yes.
The whole cross product is by connection.
Say it again?
The whole cross product is by connection. Just like that.
No. To find a bijection, I have to say where this goes. Where do you map 0, 0? 1. Where do you map 0, 1? 2. Where do you map 0, 2? Say it again?
Not
3?
No, not 3. You want to go diagonal.
Right. Very good. So the idea is that really what is countable is what you can write on a line, one after another. And so here, if you say, look, let me write this in this way. 0, 0, 0, 1, 1, 0. So I'm taking this. Now I'm taking this one. 0, 1, 1, 0. Now I'm taking this one, which is 0, 2, 1, 1, 2, 0. And then I take this one, which will be 0, 3, 1, 2.
Would you want us to actually write the opposite?
2, 0, and so on. So basically, if you write them in a line, and here you say 0, 1, 2, 3, 4, 5, 6, this is the injection and the bijection, right? And so here the clever idea is to move on the diagonal to make sure that you count each one and you don't forget any. And so Cantor had this one. It is relatively surprising. If you have a bijection, means that the number of elements in one set and the number of elements in the other set, basically they are the same. For each one here, there is one here, and for each one here, there is one here. Exactly. And so, he had this diagram here, where you have all the pairs. This is from Wikipedia, so if you go there, you see the same. And he does this diagonal and finds all the elements. All right? So there are some interesting consequences of this. If you have a countable union of countable sets, this is countable. Why? Well, because this line is countable, and the next one is countable, and the next one is countable, and there is a countable number of lines. Every language, including C and Java, is countable. How would you argue that the C language or the Java language are countable? Here you have the set of all the C programs. How do you put it in a bijection with the natural number? Well, first, consider all the C programs which have length 1, only one character. Of course, there is none. You sort them, and you write them one after another. Then, all the C programs that are 2 characters, you sort them, and then all the C programs that are 3 characters, and 4, and 5, and 6, you sort them. basically you write a dictionary of all the C programs. They are written in a straight line, one after another. You don't forget anything. This is the byjack. Basically, everything that you can write one after another is countable. All right? So far so good? Not a very difficult concept. Let me repeat what we did here. We said that when a set is countable, we said when a set is countably infinite, basically a set, speaking with my hands, is countably infinite when you can write all the elements one after another. And so we saw that some set, like all the pairs, you can write them one after another. And so it's countably infinite. C programs, you can write all the C programs one after another. So it's countable. So the question is there anything that is not countable? Yes? Yes.
So the example says set A is countable if there's injection to specifically the natural numbers.
Yes.
In the example of C++, there's things that are countable with, as long as they're an injection to something, like it doesn't have to be the natural numbers, it could be the language C++, for example.
Yes, but I'm not sure why you want to change it.
I was just because it was, so the sets that are countable are not limited to numeric sets.
Right, so here is the set of pairs, it's not numeric.
Okay.
And the C programs, of course, are not numeric.
Okay.
They are strings. C++ is a set of strings, right? Yes.
Just clarifying.
Yes. Thank you for clarifying. Yes. So the question is there anything that is not countable? And actually there is. And I will show you very quickly that there is something which is not countable. So something that is not countable is the set of all the infinite strings over 0 and 1. Typically when you say string, even if we don't say anything, we think finite. So to make sure that we understand, we say infinite strings. When we talk about sets, we don't say infinite set or finite set. When we talk about set, typically it can be infinite, even if we don't say it. With string, typically we make the opposite convention. And so we do this one. So now I'm going to show you that you cannot write all the strings one after another in a line. This is a difficult proof, conceptually. Why? Because now I try to write all of them in a line, and I'm not going to do it. And you could say, because you are an idiot. Someone smarter than you comes along, and she will be able to write all of them in a line one after another. So I had to prove that there is no one smart enough to be able to write them one after another, all of them, right? So let's do it this way. Suppose that someone is smart enough to write all these elements, all these strings one after another. So one string will be 0, 0, 1, 0, 1, 1, 0, 0, 1, and so on. Yeah? Then I write another one. This also will be 0, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, and so on. And then another one, 1, 1, 1, 1, 0, 0, 1, 1, 0, and so on. Suppose that I write all of this, all right? Suppose that I can write all of them. Now I show you that one was left out. There is one that I forgot to put there, no matter how smart I am. So first, let's see at the element of the diagonal. This is the diagonal, okay? So the first element is 0, the second is 0, the third is 1. Suppose that here there is another 1. Suppose that here there is a 0, and so on. All right? This is the sequence of the element on that diagram. You with me? Now, I flip this sequence. Where there is a 0, I put a 1, and where there is a 1, I put a 0. So this is the diagonal. This is flipped. You see how I'm flipping? Where I find a 0, I change it to a 1. Where I find a 1, I change it to a 0. Yeah? So this also is infinite. This one was not in the one I wrote there. Y is not in the one I wrote there. Can be the first? Y cannot be the first. Well, because the first one has a 0, now I flip it and I have a 1, so it can be the first. It's different. Can be the second. No, because the second is a 0 and I flip and I have a 1. Right? Can be the third. No, because I flip the third. So the F and the third are different in the third position. And F and the fourth are different in the fourth position. And F and the fifth are different in the fifth position. And F and the number 1,256,000 blah 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 differ in one position. So, what is the conclusion? Conclusion is that there is a set which is not countable. This is the set of all the infinite strings made of zeros and ones. So now a consequence of this, for example, is that the real numbers are not countable. Why? Well, if I change the first one into 0 point, and now I put that one the same that it is, this is a real number between 1 and 0, right? And I do the same with the second, and I do the same with the third. So now I have a very small subset of the real number which is not countable. Of course, the entire real number is even less countable than this. Right? Now suppose that I want to write a program that, given a real number, is telling me what are the decimal digits in the representation. People do this, for example, someone compute, I don't know, 1 billion digits of a pi. It's very easy to write a program that computes as many digits as you want of the square root of 2. So now what is the consequence? We don't have enough programs to compute the digits of all the real numbers. Why? Because the C programs are countable, but the real numbers are not. So there are not enough C programs to compute everyone. Actually, the large majority of numbers will be left out. So all of a sudden, there is a very large number of things that we cannot compute, which is the decimal expansion of the real numbers. Yes? The rational numbers are countable because they are pairs, and we saw that all the pairs are countable, right? And so now there is this very interesting and maybe slightly disturbing fact that there are things that we can't compute. One reason to understand this is that we don't have enough program to compute all the things that there are to compute. It's rather surprising. All right. So there are some consequences of this, because there are some structures that we can map to these strings. Sorry, you are not seeing it. I see people are starting to move to leave. Of course, this is like a movie, that there is a close to the end scene where you learn everything and this was interesting, but we keep going. The movie is not over. So there are some consequences of this. One is that the real numbers are not countable. The other one is that the 2 to the n, the power set, is not countable either. Because you can make a bijection between the power set and these strings of 0 and 1. I'm not going to do it, but if you go on Wikipedia, it's relatively easy to see. The other one is the set of all languages over an alphabet is not countable. One language over an alphabet is a set and is countable. So if you take the ASCII alphabet, all the C programs is one language over this one and is countable. And all the Java program is a different language and is countable. But the set of all the languages, C and Java and Fortran and Ruby and Python, all the languages, that is not countable because again, you transform it into this. Another interesting point is the set of all sets. The set of all sets doesn't exist. Why? Well, we don't consider the power set of this one that we know is not countable, right? So the power set of S would be, on the one hand, an element of S, because it's a set. And so we would have the power set would be both bigger and smaller than S. So we get this contradiction. And so we have to be very careful when we make sets. Now, if we go back to the lecture where I told you what was a set, I cheated a little. Because my definition really didn't prevent you from making the set of all sets. So now we have to be a little bit more careful. And a good point is that when you make a set, make sure that all the elements are of the same kind. So, if you have a set of integers, all the elements are integers, you don't run into any problem. If all the elements are strings, you don't run into any problem. If the elements are sets and you can put there any sets, then you run into trouble. Alright? So this is a good point to stop. And next time we will come something very different that we are going to use to discuss probability.